Part 5 of complex numbers, we are looking at exponential form and de Moivre's theorem. So we've seen polar form, we've seen rectangular form. Now, Euler's formula says the following. For all thetas, e to the power I theta is equal to cos theta plus I sine theta. A very lovely formula, but how does it help us? Well, we already know we can represent a complex number as r cos theta plus r times I sine theta. Well, that means if we look at Euler's formula, e to the I pi, that's r times cos theta plus I sine theta, which is r times e to the I pi, I theta, So that means if I've got a complex number in polar form, so if I know z is equal to r cis theta, I can represent it in exponential form as r times e to the power I theta. So it's another representation that helps us with some other calculations, but we're not going to spend too much time on this representation. So we've got r times e to the power I theta. So if I've got z in rectangular form, minus root 3 minus I, now we've already seen in polar form, that gives me 2 cis minus 5 pi over 6. So in exponential form, that will be 2 times e to the power I times minus 5 pi over 6. So there's no calculations involved, changing from polar to exponential form, just rewriting r and theta. So you just need to know the formula and be able to rewrite it. So there's no calculations involved, but just be aware that this is another representation of complex numbers. All right, so let's see what we're going to do from here. If I've got two complex numbers in polar form, then we now have a formula for multiplying those numbers or dividing them, where the product is of these two complex numbers is r1 times r2 cis theta 1 plus theta 2. Now there's a couple of ways to show you where this comes from. The quickest way I find is if we rewrite them in exponential form. So this is r1 times e to the power I times theta 1. And this one is r2 times e to the power I times theta 2. So if I want to multiply z1 times z2, it's r1 e to the power I theta 1 times r2 e to the power I theta 2. Now that we know is r1 times r2, and we add the exponent, so it's e to the power I to the times theta 1 plus theta 2. So that's a nice way to show. So if we write that back into polar form, we get r1, r2 times cis theta 1 plus theta 2. And similarly for division, r1 divided by r2, and we subtract those as we do subtract exponents. All right, so let's see how this is going to help us. This is leading to what is called de Moivre's theorem, but let's get started by just a small thing. If I got 1 plus I times minus 1 plus I. Now this is yet again a simple example to show the concept. It can be expanded to more complicated examples. If we multiply that out, we get minus 1 minus I, which is minus 2, minus I, which gives me 0, so it's minus 2. So I've got minus 2. Now if I have to write these in polar form, we already know, we've seen that in a previous video, that's root 2 cis pi over 4. If you didn't see that or don't remember it, you can pause here and make sure you can convert them to polar form, because that's always important. Times root 2 cis 3 pi over 4. So the previous theorem we saw, we multiply those, so it's root 2 times root 2, which give me 2. Cis, we add the angles. So it's pi over 4 plus 3 pi over 4. So that gives me 2 cis pi. So just for our curiosity, where's 2 cis pi? It's over here. That distance is 2, so it's the value minus 2. So that looks the same as what we've got there. All right, so the two calculations, not one was much easier than the other or quicker than the other, but this is getting us to helping us do some things quicker. So let's just do this one. If I had to divide them, and I'm not going to do it, but I suggest you do the calculation, times it by the complex conjugate, and you will get minus I. All right, so that's something for you to go practice and test that you get it. If we had to write it in terms of polar form, that's root 2 cis pi over 4 divided by root 2 cis 3 pi over 4. Now we divide the root 2 and the root 2 and we get 1 cis, and we subtract those. And that gives me cis of pi over 4 minus 3 pi over 4 is minus pi over 2. So where would that be? That will be over here. The distance is 1. So on the imaginary axis, that gets us to the point minus 1, and that's minus I. So we're happy that those two methods give us the same answer. So why do we prefer this polar form? Well, for the following. What if I had to multiply 1 plus I 4 times? Then then it becomes very tedious. It's fine just doing one multiplication, but if I've got to multiply and multiply and multiply, I've got to each time do 4 calculations, it gets a bit messy. So why do we not use this formula we have now to help us do something like this? So that gets us to the following portion. And that says, the Moivre's theorem says, if z is equal to r cis theta, then z to the power n is r to the power n cis n times theta. So we're not proving this one, but let's just get some support for this. We said if I've got root 2 cis pi over 4, that's what we now want to multiply with itself 4 times. So we carry on 4 of these root 2 cis pi over 4s to multiply it 4 times. The first two we know, we multiply those two. So it's a root 2 times a root 2 cis, and we add those, pi over 4 plus pi over 4. But now there's 2 more. Let's multiply those 2. And this is times root 2 times root 2 cis, add those 2. So if I just sort these things out, get like terms together, I get root 2 times root 2 times root 2 times root 2. How many are there? There's 4 of them. So it turns out to be root 2 to the power 4. Cis, 1, 2, 3, 4. Pi over 4 plus pi over 4 plus pi over 4 plus pi over 4. So how many of them are there? There's 4 of them. Cis 4 times pi over 4. So that supports the theorem we've seen. All right, it doesn't prove it, it just supports it for one example. So when we have to raise a complex number to a power, please use polar form, because a rectangular form takes way too long. So if we look at this example, 1 plus I to the power 4 is the same as root 2 cis pi over 4 to the power 4. How do we do that? Well, it's root 2 to the power 4 cis 4 times pi over 4. So what is root 2 to the power 4? That is just 4. Cis 4 times pi over 4 is pi. So that is how we raise a number to a power. But it has to be in polar form. That's way easier. So let's look at this last example here. 2 cis pi over 3, that's w. If I want w to the power 6, simply using the Moivre's theorem, that's 2 to the power 6. Let me just write that out. W to the power 6 is 2 to the power 6 times, or 2 to the power 6 cis 6 times pi over 3. And we can simplify that. 2 to the power 6 is 64. We don't have to take it to 64. We can leave it as 2 to the power 6, but that's cis 2 pi. And there we go. So that is using the Moivre's theorem, and especially in polar form.